into it. We're starting on modules, and soon we're gonna do Hello World, I guess. Right, so modules. We're gonna load some modules. A Haskell module is a collection of related functions, types, and type classes. A Haskell program is a collection of modules where the main module loads up the other modules and then uses the functions defined in them to do something. Having code split up in several modules has quite a lot of advantages. If a module is generic enough, the function it exports can be used in a multitude of different programs. Good stuff. If your own code is separated into self-contained modules which don't rely on each other too much, we also say they are loosely coupled. You can reuse them later on. It makes the whole deal of writing code more manageable by having it split into several parts, each of which has some sort of purpose. They call them libraries in C, right? The modules. Wait, woo, JavaScript. The best command line interface apps are made in JavaScript? Wait. You're messing around, right? JavaScript for a command line interface? I thought JavaScript was just for the web. Right? Connected with HTML and CSS, and there you go. HTML5 or whatever they call it. Isn't that the whole point? Right, it makes the whole deal of writing code more manageable by having to split into several parts, each which has some sort of purpose. We like that. Purpose. The Haskell standard library is split into modules. Oh, a library is a collection of modules. Right. Each of them contains functions and types that are somehow related and serve some common purpose. There's a module for manipulating lists, a module for concurrent programming, a module for dealing with complex numbers, etc. All the functions, types, and type classes that we've dealt with so far were part of the prelude module. Oh, that's why GHCI was saying prelude, because that's the main module, so to speak, which is imported by default. Yeah. In this chapter, we're going to examine a few useful modules and the functions that they have. But first, we're going to see how to import modules. Now Runner says, I'm not messing around. This dystopian future is now. I saw a video by, what's he called? Engineer Man? Yeah, he made a tier list for all the best languages in 2021. JavaScript was S tier. JavaScript and C was S tier. It was kind of funny. Right, the syntax for importing modules in Haskell script is import and then module name. Oh. That's it, alright. Time for the next chapter. Wait. It's longer. I thought we were done now with the modules. No, I'm just kidding. Right. This must be done before defining any functions, so imports are usually done at the top of the file. One script can, of course, import several modules. Just put each import statement in a separate line. Let's import the data.list module, which has a bunch of useful functions for working with lists, and use a function that it exports to create a function that tells us how many unique elements a list has. Tokens, right? Yeah. Right, import data.list. All right. Num uniques. Wait, this is something we create? No, wait. Number of uniques. We check for equality. Yeah, of course. check if something unique, we have to be able to check for equality. And we take a list of something and we return an int. That is how many exactly. So length dot nub. Wait. Alright, we take the length of the resulting list, right? I'm assuming nub is something interesting. When you do import data list, all the functions that data.list exports become available in the global namespace, meaning that you can call them from wherever in the script. Nub is a function defined in data.list that takes a list and weeds out duplicate elements. Why nub? No. Duplicate? No duplicates? I have no idea. Alright. Composing length and nub by doing length.nub. Yeah, we compose them, right? Produces a function that is the equivalent of checking the length. Yeah, we remember this from yesterday. We compose them. We nub the list, take everything off, and then we check the length, how much is left. Yeah. Duplicating elements is pretty nub. Noob! Noob. Noteowner says, I've been enjoying trying a few betas and reporting Linux-specific issues to the developers. So hopefully they'll be fixed before the game ever makes it to release. Nice. Have you gotten any responses yet? Maybe that's... Wait, that's a bit quick. It's Monday today, isn't it? Tuesday? I don't know. Give them a couple of days, right? Weeks, months before getting to it. That's very kind of you, Noderunner, yeah. Helpful indeed. Right, you can also put the functions of modules into the global namespace when using GHCI. If you're using GHCI and you want to be able to call the functions exported by data.list, do this. Oh, I don't import? I thought I was just gonna type import, but no, we take :m plus data list. Wonder what M stands. Oh, plus module. No. Yeah, module, and we add the data list. Okay. If we want to load up the names from several modules inside GHCI, we don't have to do m plus several times. We can just load up several modules at once. Yeah, get all of them. However, if you've loaded a script that already imports module, you don't need to use the m plus to get access to it, right? We can just load the module and the import comes with the module. If you just need a couple of functions from a module, you can selectively import just those functions. If we wanted to import only the nub and sort functions from data list, we do this. Now we use import. Why? All right. I feel I need some clarity here. All right. EHCI and import data.list. I suppose the whole point of doing it this way is that we can, instead of writing it multiple times. Now we're not in the GHCI. Wait, you mean here? Yeah, GHCI is just a preload, you mean? Now we're somewhere else. We've built a new interactive environment. Is that it? Oh, right. We're not in GHCI in the book. Right, not yet. But this works. I was kind of thinking that this was gonna work, so it did work. Yeah, the :M is in GHCI. That thing can't use in code. Yeah. This is specific for the interactive shell, right? This is the interactive environment. This is an actual file. Like :T, yeah. Right. And we can just import the ones that we need, which is the best way to do things, I guess. You can also choose to import all of the functions of a module except for a few selected ones. Oh, that's nice. That's often useful when several modules export functions with the same name and you want to get rid of the offending ones. Oh, right. Say we already have our own function that is called nub. Get good, nub. And we want to import the function from data.list except the nub function. And we can probably import nub as something else. Yeah, just like in Python. All right. So here we just add a list of what we want to do. We can hide nub. Another way of dealing with name clashes is to do qualified imports. The data.map module, which offers data structure for looking up values by key, right, exports a bunch of functions that with the same names as prelude functions like filter or null. Why would they do that? If prelude is automatically... If prelude is the functions that those are the built-ins, right? We always have them. Why would you have like a data map? Why would you do this? What's the point? So when we import data.map and then call filter, Haskell won't know which function to use. Here's how we solve that. That seems like a... What the... Isn't that incredibly stupid, calling them filter and null instead of calling them something else? Right. Import qualified data.map. This makes it so that if we want to reference data.map's filter function, we have to do data.map.filter. Right. If this was the way it just happened, right? If this was the standard, this would make more sense. Yeah. That's how it's done in Python, right? That you have to do data.map.filter if you want to indeed use the filter from data map, because then they won't have the same namespace. Maybe the data.map creators couldn't come up with synonyms? Yeah, but it's important. It imported to the Haskell structure, right? Someone somewhere should have gone in there and just said, well, maybe change these names or have this functionality be the standard. No? Maybe. We'll get in on tab says, I see why people find nub offending. Colon, whatever. Wait, why do people find nub offending? Whereas just filter still refers to the normal filter we all know and love. Yeah, I like this setup. But we have to do qualified, eh? But typing out data.map in front of every function from that module is kind of tedious. It is. That's why we can rename the qualified import to something shorter. Yeah. Import qualified data map as M. Oh! Right. We don't rename the function, we rename the module. I like this, yeah. Now to reference data maps filter function, we just need to use m.filter. Exactly, this is what I like. You just have to remember to qualify it. Weird name, all right. Use this handy reference to see which modules are in the standard library. A great way to pick up new Haskell knowledge is to just click through the standard library reference and explore the modules and their functions. You can also view the Haskell source code for each module. Reading the source code of some modules is a really good way to learn Haskell and get a solid feel for it. It's a handy reference. To search for functions or to find where they're located, use Google. A really awesome Haskell search engine. You can search by name, module name, or even type signature. Right, let's check these two out. We got a reference of all the modules, I guess. Haskell. Oh, wow, it's a bit tiny, isn't it? Let's... Oops, that's maybe better. Haskell Hierarchical Libraries. For this index includes documentation for many Haskell modules. For documentation on the GHC API, see this. Right, here we go. We got hierarchies. Let's see all the stuff we have. Wow, we're getting quite a few, eh? Right, we got control, data, debug, distribution, foreign, GHC, GHCI, graphics, language. Is that... What's this? Language, Haskell extension. What is this? All right. Haskell language dialects and extensions. This represents a Haskell language dialect. Language extensions are interpreted relative to one of the base languages. All right, so there are different versions of Haskell. So we could... Right, I was thinking... I was curious if it's like... What's it called? Natural languages or programming languages. And it seems like it's stuff to do with Haskell, not stuff we have to care about. Right. Text, however. Here we go. We have some parsing stuff. Parsec. And we got parser combinators. We got pretty print. Read text. Oh, lexical analysis. Web show, of course. And HTML. XHTML, whatever that is. Alright, so what about parsec character? Commonly used character parsers. One off. Oh, it's a parser, right? Yeah, it's for parsing stuff. Get that. Unsafe. Coerce. Coerce a value from one type to another by passing the type checker. That seems unsafe. Very unsafe, yeah. Many modules, yeah, many modules. Utilities. Containers. What are the control ones? Applicative, backwards, lift, arrow, category. Oh, concurrency. Threading. No? Yes? Control monads. Oh, our first monads, eh? Lots of monads. Holy crap. The rest of it was just controlling monads. Don't know what that is. Data, we get some array. What is this? Immutable arrays with an overloaded interface. For array types which can be used with this interface, see the array type exported by this module. Right? Type of immutable non-strict boxed arrays with indices in I and elements E. Don't know what that is. Just scrolling through here, it's not my way to learn, yeah. I mean, you can kind of, like, graphics is kind of straightforward, right? We're doing some... And we have arrays. I don't know. It's a special type of array. Array. I don't know. Right. All the stuff that we can import. Spinoza. Yeah, Spinoza created the Haskell language, right? That's how it happened. All right, a reference. Click through the standard library reference and explore the modules and their functions. I mean, I guess we get to it when we get to it. We will learn about data list today, so we don't have to do this today. All right. We have Google here, where we search for functions to find out where they're located. Name, module name, or type signature. Oh, right. So Google is a Haskell API search engine which allow you to search the Haskell libraries on Stackage, either by function name or approximate type signature. More nubs. Ah. Right. This seems kind of interesting. Yeah, Google. What if we search for map? Wow, we got a lot of different people calling stuff map. Okay. I get it now, right? If everybody's calling everything map, then you don't have to care about trying to be unique name stuff, right? Alright, let's try to remember about Google for the future. I mean, the name is catchy, I guess. Data.list. The data.list module is all about lists. Obviously. Pretty straightforward. It provides... Well, this song is messing a little bit with my concentration. It provides some very useful functions for dealing with them. We've already met some of its functions like map and filter because the prelude module exports some of the functions from data list for convenience. Oh, so the reason why they have the same name is because they are the same function. Is that it? Is that why they have the same name? Map and filter? You don't have to import data.list via a qualified import because it doesn't clash with any prelude names except for those that prelude already steals from data.list. Alright. Then it makes sense that it clashes and why we don't have to bother or care about it. So not so stupid after all. Let's take a look at some of the functions we haven't met before. Alright, so now we're just listing through another set of functions that we can do. Intersperse takes an element and a list and then puts that element in between each pair of the element of the list. Here's a demonstration. Monkey. Oh, intersperse. Yeah. Pretty straightforward. You put this element and put it as in between every other, yeah. Intercalculate takes a list of lists and a list, then inserts that list in between all those lists and then flattens out the result. Hmm. A pretty good, pretty cool function, yeah. Transpose. Transposes a list. If you look at a list of lists as a 2D matrix, the columns become the rows and vice versa. Ooh. Ooh, I like that. Transpose. Yeah. Yeah. 1, 4, 7, 2, 5, 8. And 3, 6, 9. Like that. This doesn't look very helpful though, but yeah, when you do 2D data structures, having so you can work, you can flip it around and work. I like that, yeah. Say we have the polynomials. Oh no. Math. Okay, that's... I recognize this structure a little bit. Yeah. Polynomial. They swing around, right? They have a couple of turns. And we want to add them together. We can use the lists. Wait, what is happening here? 0, 3, 5, 9. Then 0, 0, 9. I'm very confused to represent them in Haskell, right? Now all we have to do, map some transpose. Oh, right. Yeah. 10 plus 8, 18. When we transpose these lists, this third powers are then in the first row, the second power is in the second row, and so on. Yeah, mapping sum to that produces our desired result. Yeah, I guess that's one way of doing it. Okay. Wait, here we go. Fold left and fold left 1 with an apostrophe are stricter versions of their respective lazy incarnations. Oh, stricter? When using lazy folds on really big lists, you might often get a Stack Overflow error. The culprit for that is due to the lazy nature of the folds. The accumulator value isn't actually updated as long as the folding happens. What actually happens is that the accumulator, that I forgot that name yesterday, accumulator. What actually happens is the accumulator kind of makes a promise that it will compute its value when asked to actually produce the result, also called a thunk. That happens for every intermediate accumulator, and all those thunks overflow your stack. The strict folds aren't lazy buggers and actually compute their intermediate values as they go along instead of filling up your stacks with thunks. So if you ever get Stack Overflow errors when doing lazy folds, try switching to their strict versions. I kind of feel, why are we getting this here? Why is this relevant? Is it part of the data.list module that we have to import fold these from data. Wait, what was it called again? Data.list. Yeah. Right, we can import these from data.list. I get it now. I got a little bit confused because of... But yeah, they are functions that are in data.list. Concat flattens a list of lists into just a list of elements. Oh yeah, pretty good. Get this and just turn it into a single one. No list of lists. Yeah, Colgate on tab says it is in data.list. Right, yeah. It will just remove one level of nesting, so if you want to completely flatten this, you just call it twice. Yep. Doing concat map is the same as the first, mapping a function to a list and then concatenating the list with concat. Oh yeah, that looks great. And something tells me that the and is already... Oh, we can actually check. Oh shit, I did import data.list. How do I export? No, that won't work. But get rid of data.list. I suppose we can just do... Oops. And this. And we can do... And... Yeah. Thought and was already gonna be in there. And takes a list of Boolean values and returns true only if all the values in the lists are true. I like that. Now what makes this here? Pig step. Nice. What are we looking for? True only if all the values in the list are true. Yeah. So, right. And wait, I'm confused. Oh, right. We map, are they greater than 4? They all are, therefore true. And then we check, are they all equal to 4? No, they're not. So we return false. This is just so we don't have to do parentheses. I kind of like the dollar sign. It makes it... I could get used to this, the dollar sign. Definitely. What was the other one? The dot operator. Where we took function... What's that? We put two functions together with the dot operator. Don't remember the name for it. I'm terrible with names. Alright. Or it's like and, only it returns true if any of the Boolean values in the list are true. But we have nor as well. Any and all take a predicate and then check if any or all the elements in a list satisfy the predicate, respectively. Usually, we use these two functions instead of mapping over a list and then doing and or. All right, any for true, yes. Right, because any will stop. You won't iterate all over the entire list. Yeah. If we have 4 as the first element in the list, we will return true immediately. Wait. Which way? Yeah, exactly. All will go over all of them though, but I guess that's easy. Right. Iterate takes a function and a starting value. It applies the function to the starting value, then it applies that function to the result. Then it applies the function to that result again, etc. It returns all the results in the form of an infinite list. Oh. Alright, we take 10. Good, otherwise we cannot print it. That's why we take 10. So we iterate, multiply by 2, 1. So that times 2, that times 2, that times 2, that times 2, that times 2. Yeah, exactly. Okay. Split at takes a number and a list. It's then splits the list at that many elements, returning the resulting two lists in a tuple. I like that. I wonder why you have to name it split at. Oh, right. That's pretty good. Because of how the syntax does the stuff that I have. Oh, it's called function composition when you put two functions together. Yeah. Thanks, Colgate on tap. In Haskell, it's pretty important that the functions are named pretty good. Naming it just split wouldn't imply that we need a value to split at, right? That this function... Yeah, that you need two parameters in split at. You need where to split and the list to split. And it becomes easier to see if you name it split at instead of just split. I guess, is there something just named split? Nope. Actually, I don't think split at is probably not important. No, it is. It's part of prelude. Yes. Take while is a really useful little function. It takes elements from a list while the predicate holds, and then when an element is encountered that doesn't satisfy the predicate, it is cut off. It turns out this is very useful. Ooh, yeah. That looks very useful, yeah. For parsing. Looks very useful indeed. They wanted to know the sum of all third powers that are... He doesn't even go to parsing. He goes to maths for some reason. Didn't we have that already? Take while? I think maybe we did. I kind of felt like a twinge of remembrance as well, Colgating on tap. So we probably did. It's, however, it's a really useful little function. So it's worth pointing that out again, right? I won't remember this function in a couple of days. So it's a good thing to repeat it, I would say. Yeah. Alright, say we wanted to know the sum of all third powers that are under 10,000. We can't map to this. Wait, apply a filter and then try to sum that up, because filtering an infinite list never finishes. Yeah, that won't work. You may know that all the elements here are ascending, but Haskell doesn't. That's why we do this. Take while... Alright, yeah. Wonder if we used this example before as well. Don't remember. Right, we... What is this called? I know the 2 is called square. We cube? Ah, yeah, we cube. We cube all the elements in an infinite list, and then once an element that is over 10,000 is encountered, boom, we cut the list off. Now we can sum it up easily. Lovely. Drop while is similar, only it drops all the elements while the predicate is true. Once the predicate equates to false, it returns the rest of the list. An extremely useful and lovely function. Yeah, it's the same, it's just the other way around. Flipped, if you will. Maybe not flipped, but... Alright. We're given a list that represents... Wait. Oh, we're talking about drop while. Stock by date. The list is made of tuples, whose first component is the stock value, the second is the year, the third is the month, the fourth is the date. We want to know when the stock value first exceeded $1,000. Alright, so we'll let this be the stock. We got tuples. And we just went with val. Alright, we decided what that it is val. When it's higher than 1,000, which is over here, right? Yep, val. We check when that is higher. All right, we drop everything else, right? So all of these are gone. Since we get the date with it. That's great. This book is old, isn't it? It's super duper old, but kind of old. Span is like it's kind of like take while. It only returns a pair of lists. The first list contains everything the resulting list from take while would contain if it were called with the same predicate and the same list. The second list contains the part of the list that would have been dropped. Oh. Wait. So it's kind of like both of them, but we get a tuple with both values, right? So this just takes the first bits of the list. This just takes the second bits of the list. This gives us both of them. We get them as two separate. Whereas span spans the list while the predicate is true, breaks it when the first predicate is true. Doing break P is the equivalent of doing span not and then P. Okay. Wait. Oh, right. This is, we check for each element in span. Wait. Yeah, they very similar. We break at the 4. And here we break. No, we keep running as long as we don't run into a 4. There we go. So break, we'll look at a specific breakpoint. While span, we look for... We want to keep all these things. Alright, when using break, the second list in the result will start with the first element that satisfies the predicate. Yep. Sort simply sorts a list. The type of the element in the list has to be part of the ORD type class. You know that. Because if the elements of a list can't be put in some kind of order, then the list can't be sorted. You've seen that before. Group takes a list and... Wait. Takes a list and groups adjacent elements into sublists if they are equal. Adjacent elements into sublists. Only if they are equal. Okay. Yeah, we got the 2's here and the 2's here. If we sort a list before grouping it, we can find out how many times each element appears in the list. Indeed we can. Inits and tails are like init and tails, only they recursively apply that to a list until there is nothing left. Observe. Oh, right. Nothing? Then it's... And tails does the same thing, but flipped. That's interesting. Don't know why I would want to do that, but I can imagine. What? Funny, yeah. Let us use a fold to implement searching for a sublist. Wait, needle in a haystack. What are we trying to do here? check for equality if take two lists and return if they're true. Okay. Let length of the needle. Wait. I'm confused. What are we doing? Right, if x is equal to needle. No, we take the length of the needle. Wait, what are we trying to do? Or sublist. We're looking for a nail in a haystack, but for some reason we're looking for the length of the nail. Why do we care about the length of the nail? Right. Accumulator X. If take the nail length. Right. First we call tails with the list we're searching. Then we go over each tail to see if it starts with what we're looking for. That we've actually just made a function that behaves like is infix off. Is infix off searches for a sublist within a list and returns true if the sublist we're looking for is somewhere inside that target list. Yeah, I don't quite understand how this... It feels like, no, I don't get it. Search needle in the haystack where we let... Yeah, the length of the needle. Why do we care about the length of the needle? Oh, because we're looking for if it starts with, right? Right, we see that it's... Wait, no. Why would we need the length of it anyway? Oh, because we only need... Right, we don't know how many items we need from here. We need the length to say when we find the first, we need to check for two more. That why we need the length? Because sublist can only be equal if it's mass, same length. Has, same length. Yeah, exactly. It can only be equal if we have the length. Yeah, exactly. So that's what we do. We find the first, and if we find a C, then that's when we do the check, right? We check... Yeah. We take... when we have the length. And if it then becomes equal... Okay, that's confusing. Alright. False, true. Oh, right, we only check if it exists within. Is in... infix off. Is prefix off. Is suffix off. Oh, they are... Yeah. Search for a sublist at the beginning and at the end of the list, respectively. Kind of... I think the word search throw me off a little bit, right? I mean, it is searching, but it's kind of... It's... No, actually. We don't... Like, I was thinking that we're looking for a list within the list, right? I thought we would, like, we have a list. Nope. Okay. I don't know. How many was that? And one more. Well, this was needlessly difficult, right? If we have this list here, I don't even know if I put it. Oops, 1L too many, eh? And there we go. I thought that if we were searching for a sublist, I thought we were looking for this. But that don't work, because that you can't do this in Haskell. Yeah, you can't do that in Haskell. Because a list has to have the same elements, right? If you have a list of lists, right, it all has to be the same type. So that was, yeah, search for sublist confused me. Because we kind of create a new list, right? This is a new list that we created, and we check if that exists within this. Right, and we check prefix, suffix, they are the same. It's just the first and the end. If it starts with or ends with. Yeah. Element and not element, check if an element is or isn't inside a list. We have done that before. Partition takes a list and a predicate and returns a pair of lists. The first list is the results, contains all the elements that satisfy the predicate, and the second contains all the ones that don't. Didn't we have something else that pretty much did the same thing before? A span is similar to partition, right? Similar. It is important to understand how... It is important to understand how this is different from span and break. All right, why is it different? All right, we partition if we find an element. Oh, right. We go through all of them, right? We take all of the Bob Morgan, exactly. We take all the big, all the capitalized stuff, because all of them satisfy this thing. While in span and break, we find a spot. The first time we find something. Yeah. While span and break are done once they encounter the first element that doesn't and does satisfy the predicate, the partition goes through the whole list and splits up according to the predicate. Indeed. Find takes a list and a predicate and returns the first element that satisfies the predicate. But it returns that element wrapped in a maybe value? What's a maybe value? We'll be covering algebraic data types more in depth in the next chapter, but for now, this is just what you need to know. A maybe value can either be just something or nothing. That seems like cheating. Yeah. That seems like cheating. I remember reading, wasn't the whole point that we always have to return something? So returning a maybe is kind of weren't they like early chapters talking about you can't return nothing. Everything has to return something. Even if it's an empty list or not a value or whatever, but maybe we do have to do some cheating. Much like a list can be either an empty list or a list with some elements, a maybe value can either be no elements or a single element. Alright, we're just dealing with lists, right? So, right, no, we're not returning nothing. We're just returning an empty list, right? We just do... right. Can we do this? No. Wait. That won't work. This. Nope. That's not the one I was looking for. Yeah. Yeah, the element can be nothing. That doesn't break the list. We still have a list, right? Even though this specific value is nothing, right? If we don't find anything, it has to be nothing. Yeah. Right, and like the type... Wait, and like the type of a list of, say, integers is int, then the type of maybe having an integer is maybe int. Yeah. Anyway, let's take our find function for a spin. Yeah. Oh, a predicate. Right, yeah, predicate. Wait, just 5? Oh, just something. All right. Just 5 or nothing. Why not 6? Because find just returns the first value. Yeah. When you find 5, we're done. We don't iterate. We're lazy. We don't care about the 6 anymore. Right, sure. Yeah, we take function that goes for an item and... No, a function that returns a boolean, which we apply on a list, and we return maybe what exists in the list. Or we returns nothing. Kinda. Colgatino tab says it is a container like lists and tres and such. Oh, trees. Well, I've never worked with trees. I guess we'll get to it. It's a container that has nothing. Well, a maybe is a container that maybe has something. The naming convention is spot on, right? Maybe a. I love that. It's spot on. It explains exactly what it does, right? We find maybe an a, or we do, or we don't. We have to prepare for both possible outcomes. That's what we have to do to be functional. We have to prepare for both outcomes. We have to prepare for the outcome that we don't find anything. Yeah. Remember when we were searching for the first time, our stock went over 1,000. We did... Oh, I didn't remember this. We did... Wait. And we took the stock. For the stock, we had this function, right? We've... Yeah, we dropped while the value was lower than 1,000, exactly. Remember that head is not really safe? Don't remember that. Why is head not safe? What would happen if our stock never went over? Oh, wow, yeah. That would be a problem. Our application of drop while would return an empty list, and getting the head of an empty list would return in an error, because there is nothing there. However, if we rewrote it as find, instead of drop while, we just try to find, because it returns the first value. Assuming that the ordering of the list is chronological. Right? If something came in the wrong order, this wouldn't help. We would miss out, wouldn't we? We could sort it based on date before if we needed to, yeah. Would be much safer if our stock never went over 1,000, so if no element satisfied the predicate, we'd get back nothing, yeah. But there was a valid answer in that list. We'd get, say, just, and this thing. elem index is kind of like elem, only it doesn't return a Boolean value. It maybe returns the index of the element we're looking for. Nice, I like this one. Elem index. Oh yeah. If that element isn't on our list, it returns nothing. Definitely like that. Wait. We have many things left to go? Yeah. Alright. Let's keep going through these tomorrow, yeah. So many of them. So many functions. I'm not remembering any of these. But when we run into them into the wild, there is a heightened possibility that we will understand these functions since we have went over them. Shit. Where were we? Yeah. Heightened chance. You will remember nothing, right? I will remember it. The maybe value. When I run into the maybe value, I will get a tinge of remembrance and I will maybe understand what I'm looking at. Or maybe I will remember nothing. But even if I don't remember anything, it will be easier to reach understanding because we have looked at it once, right? But yeah, that's it. That is lunchtime. Yeah, so thanks for hanging out and have a good one. And see you next time. Yeah, cheers.